You know, we always talk about the universes, but the mysteries like black holes and supernovas and all that, but um, sometimes the most profound questions come from the tiniest places, you know?
It's true.
And that's where our deep dive takes us today, the world of right-handed neutrinos.
Yeah, it's true. These particles, I mean, they're completely invisible to us, at least directly, but they could really hold the key to understanding some of the biggest questions about our universe.
Absolutely. And we've got some seriously dense research here. So to set the stage, let's talk about the standard model of particle physics. Basically, it's our best attempt at a map of all the fundamental particles that make up, well, everything.
Yeah, and it's an incredibly successful model. It really explains so much about how particles interact and how they form the universe as we know it. But like any map, there are still some blank spots.
Yeah, and one of those blank spaces, one of the biggest head scratchers for physicists, is this question of neutrino mass. The standard model, as it is right now, doesn't really explain why neutrinos, these super tiny, almost ghostly particles, actually have any mass at all.
It's true, and we've known for a while now from things like neutrino oscillations, experiments with those, we know that neutrinos do have a tiny amount of mass. But the standard model, at least in its purest form, it just doesn't account for it.
So you might be thinking, okay, neutrinos have a tiny mass, so what? But here's where it gets really interesting. Understanding this could help us understand huge mysteries like dark matter, the stuff we can't see but we know must be there, and also the imbalance of matter and antimatter in the universe.
Exactly. It's like we're missing a piece of the puzzle. And that's where these right-handed neutrinos come in. These hypothetical particles, if they exist, might be that missing piece.
Yeah, it's like finding a hidden doorway in a house you thought you knew like the back of your hand. So how do we even begin to study these particles if they're, well, hypotheticals?
And that's where these NR-EFTs come in. Imagine you want to study like the effects of a creature, but you never actually get to see it. You never see it directly. You might look for footprints or broken branches, maybe droppings, things like that. And that's kind of what NR-EFTs let physicists do.
Okay, wait, back up a bit. What exactly does NR-EFT stand for?
Right, sorry. So it stands for right-handed neutrino effective field theories. Basically, they're a set of tools that let physicists explore the effects of right-handed neutrinos without directly observing them.
So like we were saying, searching for clues instead of the whole picture.
Precisely, yeah. With NR-EFTs, physicists can build models and make predictions about how these right-handed neutrinos would interact with particles that we already know about. And then they can compare these predictions with real experimental data.
Okay, so that makes sense. So where do these operators we see mentioned in the research, where do they fit into all of this?
Ah, yes, the operators. Think of them like verbs in the language of particle physics. There's essentially mathematical terms that describe how particles interact with each other. And that includes how these right-handed neutrinos might interact as well.
And these operators have different dimensions. I mean, that sounds awfully sci-fi, doesn't it?
I know it sounds like we're talking about parallel universes and stuff, but it's actually a lot simpler than it sounds. The dimension of an operator is basically just a way to categorize how complex it is. So you have dimension 5 operators, which describe these simpler interactions, and then you have dimension 6 operators, and those are a bit more complex, a bit more intricate.
Got it. So it's like saying, I don't know, walk versus walk quickly. They both describe walking, but the second one has a bit more detail.
Exactly. And then another thing the research talks about is loop suppression. And essentially what that means is some of these interactions, even though they're technically possible, they're about as likely as, like, winning the lottery twice in a row.
So astronomically rare, even if they're technically allowed.
Exactly. Now, with all that said, the big question is, if these right-handed neutrinos actually exist, how would we even find them?
Right, because if they're that rare and they interact that weakly, I mean, just finding evidence of them seems like a monumental task, to say the least.
Yeah, it is. But physicists are a clever bunch, and they have a few tricks up their sleeve. One of the most promising ways to discover these right-handed neutrinos is through particle colliders.
Like the Large Hadron Collider, the LHC, that's the one that smashes protons together at almost the speed of light, right? What would physicists even be looking for in those collisions?
You're right, that's the one. The paper suggests that if right-handed neutrinos are produced in these really high-energy collisions, they decay almost instantly. They leave behind these telltale signs in the debris of the collisions.
So it's like trying to figure out what a firework was made of based on the pattern of sparks it leaves behind.
That's a really good analogy, yeah, exactly. And by analyzing those patterns, physicists could potentially find evidence of particles that only existed for a fraction of a second.
That's incredible. We're going to take a quick break, but when we come back, we'll delve deeper into these telltale signs, or I think they're called signatures in the paper. Don't go anywhere. So before the break, we were talking about how these particle colliders, these incredible feats of engineering, how they could actually help us find these right-handed neutrinos.
Yeah, and basically it comes down to looking for specific combinations of particles, things that you wouldn't expect to see based on, the standard model alone.
Like finding a penguin in the Amazon rainforest or something. Something unexpected is up.
Haha, yeah, that's a great analogy. So the paper we're looking at, it dives into three main types of collisions that could potentially, show us these right-handed neutrinos. Proton collisions, and of course those are the ones happening at the LHC. Then you've got electron-proton collisions and electron-positron collisions.
So a multi-pronged approach, casting a wide net, so to speak.
Exactly. Each type of collision has like its own pros and cons, its own advantages and disadvantages in terms of what you can actually detect, But let's start with I guess you could say, the workhorse of particle physics, the LHC, with its proton collisions. What would we actually be looking for in those collisions in the aftermath of those incredibly high energy crashes?
Yeah, because we're talking about smashing protons together at almost the speed of light, right? I can only imagine the chaos going on inside those detectors.
It's crazy in there.
Yeah.
But you're right. But within all that chaos, physicists are looking for these, I guess you could say, very particular patterns. They're looking for something specific. Yeah. One of the key signatures, the things that would really get their attention, would be these events with multiple leptons and some missing energy.
Okay, just a really quick refresher for our listeners. What are leptons again?
Oh, right. Good point. So leptons they're a family of fundamental particles. And this family includes things like electrons, muons, tau particles, and then you have their corresponding neutrinos as well.
Right, those super light, almost invisible particles we were talking about.
Exactly, though. So imagine, a proton smashing into another proton at almost the speed of light. And in all the wreckage, you see all these leptons flying off, but then it seems like some energy has just vanished, like it's disappeared. Yeah. And that missing energy, along with those leptons, that could be a clue, That could be a clue that a right-handed neutrino was produced and then decayed very quickly. And in that decay process, it took some of that energy with it.
Like a magic trick, but on a subatomic level. The energy just disappears, but we know something must have carried it away.
Precisely, yeah. It's like, where did it go? And then on top of that, the specific types of leptons that you see, that could give you even more clues. Like if you found both an electron and a muon together, that could point to like a specific decay chain, a specific way that a right-handed neutrino might have decayed.
So it's all about piecing together the clues, like detective work, but, on an unbelievably tiny scale.
Exactly. That's a great way to put it. Now, speaking of different types of collisions, let's talk about electron-proton collisions. And like you might guess, these involve smashing an electron into a proton.
And these are considered a bit cleaner than proton collisions, right? I seem to remember something about that.
You're exactly right, yeah. They tend to have less background noise, which makes it a bit easier to pick out those really rare events that we're looking for, those needles in the haystack. So in electron-proton collisions, the paper suggests looking for, basically they suggest looking for the production of a right-handed neutrino along with something called a jet of particles.
A jet of particles. What is that exactly?
So think of it like kind of like a mini explosion of particles. When quarks are like the building blocks of protons and neutrons, when quarks are produced in a collision, they don't just, fly off on their own. Because of the strong force, they actually create this spray of other particles. And this spray, it actually forms this narrow cone shape that looks like a jet when you see it in the detector.
Okay, so finding a right-handed neutrino along with one of these particle jets, that'd be a pretty good sign that something interesting happened, right?
You got it. Now, the third type of collision that the research explores is electron-positron collisions. And these are known for being even cleaner than the other two types. They're much more controlled.
So less of a demolition derby and more like a very carefully choreographed dance.
I like that. Yeah, that's a good way to put it. And in this scenario, in electron-positron collisions, the paper suggests looking for events where, get this, not one, but two right-handed neutrinos are produced. And each one would then decay into a lepton and a W boson.
Whoa, a two for the price of one.
Exactly. Haha, why not?
Hmm.
And those W bosons, they can then decay into other particles as well. They don't just stick around. So it creates this very distinctive signature in the detector, something that would really stand out, like finding a matched set of fingerprints at a crime scene. It's like,
Yeah.
okay, we're onto something here.
Okay, so we've got our proton-proton, our electron-proton, and our electron-positron collisions. And each one gives us a different way, a unique opportunity to potentially find these right-handed neutrinos. With all this talk about collisions and decays and everything, it makes me wonder, though, how long do these right-handed neutrinos actually exist? Like, how long do they stick around before they decay?
That is an excellent question. And honestly, that's something that physicists are really trying to understand better. The lifetime of a right-handed neutrino, it depends on a few different things. It depends on its mass, which we still don't know for sure. And it also depends on, how strongly it interacts with other particles, which is another thing we're trying to figure out.
So we're talking about incredibly short lifespans then, right? Like fractions of a second.
Oh, absolutely, yeah. We could even be talking about, much smaller timescales than that. These particles are incredibly short-lived. They pop into existence, and then almost instantly, they're gone.
Wow, talk about a race against time. So physicists are essentially trying to capture this, like the faintest whisper from these particles before they vanish forever.
That's a great way to put it, yeah. And to do that, they need to know what to look for. And that's where those theoretical predictions from NR-EFTs are so important. They give us a roadmap. They let us make these estimations like, okay, if right-handed neutrinos exist, and if they have these specific properties, then we'd expect to see, this many events at this particular collider, that sort of thing.
So it's like they're still trying to find a needle in a haystack, but at least now they have a metal detector to help narrow down the search a little.
Yeah, exactly. And what's really amazing is that, depending on the specific parameters, we could be talking about seeing thousands or even tens of thousands or maybe even millions of these events.
Millions. Wow, okay, so maybe not a needle in a haystack anymore. Maybe more like a whole bucket full of needles.
Yeah, something like that.
So we were talking about potentially seeing like millions of these telltale events, these signs of right-handed neutrinos.
Yeah, and it's not just, a vague possibility either. The paper we're looking at actually gives some hard numbers. They use those NR-EFTs we were talking about to actually estimate how many right-handed neutrino events we might see at different colliders. And for the high luminosity LHC, that souped up version of the LHC that's about to come online, they're predicting some pretty huge numbers. At least for certain scenarios, it could be really remarkable.
Okay, so not just finding a needle in a haystack, but like a whole bucket full of needles, maybe.
Uh-huh. Yeah, something like that. So for instance, if these right-handed neutrinos are produced in Higgs boson decays, and remember those are the God particles, the ones that give everything mass. If that's how they're produced, we could be swimming in events. It could be a lot to sift through.
Okay, but hold on a second. Aren't Higgs bosons themselves incredibly rare? Like finding just one is a huge deal, isn't it?
Oh, you're absolutely right. They are rare. But the LHC, it's designed to produce them. That's one of its main purposes. And the high luminosity LHC, well, it'll be even better at it. So even if only a tiny fraction of those Higgs bosons decay into right-handed neutrinos, it could still add up to a huge number of events, a really statistically significant sample size.
That's amazing. And what about the other ways we were talking about? What if these right-handed neutrinos are produced through those other processes? What kind of numbers are we talking about then?
Even then, the predictions are actually pretty promising. It depends, of course, on the specifics, things like the mass of the right-handed neutrino, how strongly it interacts, all that. But we could still be talking about seeing thousands, maybe even tens of thousands of events at the high luminosity LHC.
Wow, so it really sounds like we could be on the verge of a major breakthrough here. Like our understanding of particle physics could be about to change in a big way.
It's definitely possible, yeah. It's a really exciting time to be thinking about these things. And it's not just the LHC either. There are plans in the works for even more powerful colliders in the future. Things like electron-positron colliders and electron-proton colliders. Those are still on the drawing board. And those could offer even more opportunities, new ways of looking for these right-handed neutrinos.
It's like getting a whole new set of eyes to look at the universe with. But I think it's time to maybe take a step back here. This is a lot to take in, even for someone who's really into this stuff. So for our listeners out there, what would you say are the big takeaways from all of this? What's the big picture?
That's a good question. I think the biggest takeaway, if I had to pick just one, is that our understanding of the universe even though it's come a long way. It's still a work in progress, you know? Like, the standard model is a great tool. It's really powerful. But there's still these cracks, these things it can't quite explain. And right-handed neutrinos, they represent one of the most promising paths forward, one of the best ways to maybe go beyond those limitations, to fill in those gaps.
It's like we're standing at the edge of, I don't know, a huge unexplored territory. And these right-handed neutrinos, they might be the key to unlocking all its secrets.
I like that, yeah. It's a good analogy. And that leads to the second big takeaway, I think, and that's the power of human ingenuity. Through a combination of theoretical work, people coming up with these incredible theories and these tools like NR-EFTs, and then also through these feats of engineering, these huge particle colliders. I mean, it's mind-blowing. But we're able to study the universe at the most fundamental level, and it's really inspiring.
It is, absolutely. And it also shows how important collaboration is,
Mhm.
These huge scientific projects, they bring together the best minds from all over the world. It's like everyone working together to try to solve these huge cosmic puzzles.
Absolutely. It's really incredible to see. But, if I could add one more takeaway, and I think this one might be the most important of all, it's to never stop being curious, to never be afraid to ask questions, even if they seem kind of out there.
Yeah, because even if we don't find these right-handed neutrinos, even if it turns out we're looking in the wrong place or something, just the search itself, the fact that we're even asking these questions, it pushes the boundaries of what we know. It opens up new doors, new avenues to explore.
Exactly. Who knows what other mysteries are still out there just waiting for us to discover them, right?
Yeah, absolutely. Well, I think that's a great place to leave it. A reminder that the journey of scientific discovery, it never really ends. There's always something new to learn, always something new to explore. So thank you for joining us on this deep dive into the world of right-handed neutrinos. We hope you learned something new and maybe, just maybe, you're feeling a little bit more curious about the universe we live in.